No, pero no lo voy a ocupar, ¿no?
Ahí está.
Pero tienes que parte en
ahí la
Adobe.
Ah.
¿Funciona el clicker?
Me imagino que sí.
Es que
Vale, sí, estamos.
sí, ¿tú elegiste Adobe?
Sí, no sé.
Ah, ya.
¿No funciona?
Ah, sí, sorry. Sí. Ahí está bien. Ya.
Listo. Muy buenos días. Sean todos ustedes bienvenidos a la cuarta sesión del seminario del departamento. Hoy tengo el agrado de presentar al señor Diego Moran. Él es profesor asistente en la Escuela de Negocios de la Universidad Adolfo Ibanez. Además, este señor hizo un doctorado en investigación de operaciones en el Instituto Tecnológico de Georgia, si no me equivoco. Y además fue estudiante de Ingeniería Civil y también del máster de la Universidad de Chile. Bueno, Diego, primero, bienvenido al seminario.
Muchas gracias, Jorge y al resto de los organizadores por la invitación.
Ahora nada, muchas gracias. Bueno, como este seminario se dirige a estudiantes, siempre se parte por una clásica pregunta.
De acuerdo.
Dado que tú hiciste un máster, doctorado, ahora eres profesor asistente, has seguido toda una carrera de investigación y además vienes de una escuela de matemática tradicional, de que sigue investigación. Queremos saber tus motivaciones de por qué seguiste esta carrera, cuáles fueron tus principales objetivos cuando partiste en la investigación.
Cuando partías haciendo investigación.
Claro,
No.
después del ingeniero civil en matemáticas.
Bueno, que como decía Jorge, yo estudié ingeniería civil matemática y mientras estaba tomando los ramos de la carrera me parecía que era todo muy teórico y yo sentía que todavía una carrera realmente nueva, no está tan en boga como ahora quizás, hace 10 años era mucho menos, y dije, esta optimización se ve súper interesante porque no solamente tiene teoría, pero también tiene aplicaciones. Así que decidí tomar este magíster, porque dije, quizás me va a ayudar después para conseguir un trabajo en la industria. Y tomé el magíster, y me empezaron a interesar más los temas de optimización, en particular optimización con variables discretas, optimización entera, que se llama. Entonces me quedó gustando. Y en algún momento, después de cuando estaba haciendo la tesis, me gustó la investigación, o sea, porque además uno habla con gente de distintos backgrounds, gente que estudia ingeniería industrial, gente que estudia ingeniería matemática, o gente incluso de ingeniería mecánica, ingeniería eléctrica, que uno conoce mientras está haciendo la investigación. En particular, en mi tesis del magíster en Chile, trabajé en un modelo de planificación de la producción en la industria salmonera. Entonces no tenía que dejar harto. Lo que hicimos fue construir un modelo de optimización entera para poder aplicarlo a cómo ellos decidían cuándo cosechar o sembrar salmón en el mar para cumplir con la demanda de producción que tenían para, en ese caso, las 60 meses. Entonces el problema es súper entretenido. Y al final, incluso lo presentamos en un congreso, en el congreso uno conoce gente en muchos lados. Entonces me empezó a gustar como oye, parece que es buena idea hacer una academia, porque uno viaja, conoce gente de tantos lados, uno relativamente puede decir en qué trabajar. Y dentro del magíster se fue la oportunidad de hacer, al menos de contar con el apoyo de los académicos para poder hacer el doctorado, porque ellos son los que tienen cartas de recomendación, ellos saben a dónde uno tiene que ir a estudiar. Claro. Y eso, ¿y por qué me motivé yo a seguir investigando? Porque me gusta resolver problemas. De hecho, por eso estoy en ingeniería, me gusta intentar de mejorar las cosas, resolver los tipos de problemas de ingenio, que ocurren para muchos de ustedes probablemente en los ramos, hay que resolver algo, hay que mejorar algo, ¿cierto? Entonces, por eso me gustó la investigación y me sigue gustando. Y en el doctorado mezclé lo que hice no fue tan aplicado como este modelo que hice con la salmonella. Entonces mezclé como mi background un poco más matemático con los problemas que nacen en los aspectos más teóricos de la promoción entera. Y eso es lo que he estado haciendo hasta el momento. Entonces, y sigue siendo entretenido. Bueno, no sé si eso responde a la pregunta.
Sí, por supuesto, muy amable, Diego. Bueno,
Sí.
Diego, gracias por estar acá y el salón es tuyo. Así que,
Ya, excelente. Tenemos hasta las 1, ¿cierto?
Sí,
Ya.
teóricamente.
Ya, sí, tengo. La presentación lo voy a hacer en inglés, porque bueno, está preparada en inglés y no sabía hacerla en español, porque o saldría demasiado mal ahí, pero entonces lo voy a hacer en inglés. Ya. Okay. So this talk is about what I did first. It has two parts. First was what I did during my PhD, geodesic. And the second part is some new work that I am doing in similar unrelated topics. Okay, so the talk has, as you can see, 4 authors. Shantanu was my advisor during the PhD, and Juan Pablo was one of the co-authors of the papers. He's a Chilean professor, also working in optimization, that is now at MIT. And Gustavo Angulo, he was my classmate in Chile and also during PhD. And Burak Kojuk is another classmate from the PhD that is from Turkey. Okay, so these are the co-authors. So it's important to, because you, as I said, you work with a lot of people while doing research. Okay, so this is why I call them all co-authors, because this is mostly from work from my PhD. So there's Shantanu, he's always happy and offering donuts to people. and Juan Pablo, he was there, I think he was in Berlin at that time. Okay, so, and the new co-authors, as I said, is Burak from Sabancı University in Turkey. And I actually visited him for 1 month this summer. In February, and we work in these topics. And also Gustavo Angulo, who now is an assistant professor at Universidad Adolfo Ibanez. Okay. And this is the work that I will present at the end of the presentation. Okay. So what is this talk about? The first part, I will try to introduce the notation for what is a mixed interprogram, what is an optimization problem with discrete variables. So we all have the same notation in mind, okay, what we are going to talk about. In the second part, I will summarize in a few slides some of the problems I worked during my PhD. Okay. And in the last part, I will focus on one of the problems. And this problem is related to duality in conic mixed interior optimization. Okay. And I think most of the talk will be focused in part 3. And if you have any questions, just interrupt me in Spanish, English, and well, not in French because I don't know. So I'm looking at Jorge, for instance. Okay, so this is I call it review because I try to set the notation for the talk. Okay. So what is a mixed interprogram program? What is in this talk? So this is an example of a mixed interprogram program. So this is an optimization program where you want to optimize a function that is linear, right? So subject to some constraints, could be linear constraints, quadratic constraints, could be anything. And where some of the variables are subject to discrete constraints. For instance, x1 has to be an integer number. 0, 1, 2, 3, etc. Right? X2 can only take values between 0 and 1, so this is also a discrete constraint, right? And X3, in this case, it could be anything, any number. Okay. So these problems have a lot of application because in some models the variable has to take an integer value. For instance, how many workers have to do something, right? It cannot be a fraction of a person, right? And in particular, 0-1 variables are very useful in industrial engineering and other business applications because they are very useful to model yes or no decisions or logical constraints. So Should the track travel from this point to that other point or not? Things like that, right? So this is an example of a MIP. And in general, the definition we use is an optimization problem that where you are minimizing a linear function, right? C transpose X, right? And subject to some constraints, right? That could be linear constraint, quadratic, and others, and where we have some discreteness on the values. So those values have to be integer. Okay, and you classify MIPs according to what is the set X. So the set X, when you remove these discrete constraints, is called the continuous relaxation. Okay, and according to what is the continuous relaxation, you can classify them as convex MIP. If the set X is a convex set, or if it's a linear set, you only have linear constraints, and so on. And if this set is not convex, you have a non-convex MIP. Okay. In this talk, we'll focus only in convex MIPs because they are easier. These are much more difficult. I don't understand them actually very well. And in order to see, what I'm talking about, let me show you a picture. So, for instance, the first MIP here that in this corner is optimizing this linear function, right? Subject to some linear constraints, which are the green region, right? All the constraints here are linear, and I'm interested in variables taking only integer values, right? So those are the points of interest. So the integer points that satisfies all those linear constraints, right? So the set X, the continuous relaxation, will be the green polytope, and you're optimizing over the red points. So this is called a linear MIP because the set of constraints are linear. Similarly, you will have a convex MIP where the set is not defined by a linear continuous relaxation, but something more complicated, like a parabola, for instance. And here again, you are also interested in optimizing only the integer points with integer coordinates. And you have even a bounded convex set, right? This is again not a polyhedron because there are not only linear constraints. And the more difficult case, as I told you, when the continuous relaxation is non-convex, so it's a set that will have many different parts. So this is much more complicated. So we can forget about it. With these three, we can model a lot of applications. So that's good enough. So that's a MIP. Okay, some applications of MIPs. As you maybe know already, MIP has lots and lots of applications. In particular, these 0-1 constraints are very useful. Yes or no decisions. Right? So the applications are so important that in this organization, which is the Institute for Operations Research and Management Science, they have this award, which is considered the Nobel Prize for Operations Research. And most of the winners of the finalists of this prize are using some discreteness in their models. Okay. So these integer models are very useful in practice. Okay. And let me show you an example in finance. Okay. Maybe of interest for some of you. So this is a portfolio optimization model where what you want to do, you have your budget, your money, right? And you want to decide the fraction of your money that you will invest in each of these assets. Okay. But there is a restriction on the amount of stocks that you can have in your portfolio, right? And for that reason, you need 0-1 variables to decide whether you invest on that variable or not. Okay, so this will be this 0-1 yes or no decision. Okay, these constraints, for instance, is telling you that the sum of all ones, all yes, has to be at most m, which is the constraint, right? And other constraints that you have is, for instance, the total of your money. You need to invest the total of your money, right? This fraction must add up to 1 or 100%, right? And in addition, there is another constraint this constraint here that this represents the variance of the risk. I mean, the variance of your portfolio, because you can mind that this is random. You don't know actually, right, what is the outcome of your investment, right? So you need to have some risk associated to it, and this is telling you that the portfolio that you choose has to have bounded variance. It cannot be, I mean, too risky. Okay, and all these constraints are linear, but this constraint is quadratic because you are multiplying y, right, and transpose qy. So this is a convex MIP, a general convex MIP. And in particular, this is a conic, right? Just for you to remember that word conic, that we'll define later. Okay, so with these integer variables, you can model a lot of very interesting problems. Okay. So this is the example I have. Okay, so how do you solve these problems? Well, I mean, the short answer is that use a solver. There are a lot of software that we use to solve MIPs. There are commercial solvers like Simplex, Express, Groby, which is my favorite. Actually, it's a Chilean colleague that is working at Groby, and he works from Chile. He's the one created the code for Groby. And there are a lot of, non-commercial solvers that you can also use. Sometimes they are all what you need, but sometimes commercial solvers, since they are more powerful, you need to use them in order to solve your MIP. Okay. So, okay, how these solvers work? They have a lot of techniques, engineering, techniques that you can use to solve these problems. It's something called Bergson bound. I don't know if you have seen this already. Something that is called cutting planes. There are some heuristics, which are algorithms that are tailored to the particular problem, for instance, and so on. And in this talk, I will focus in cutting planes. Okay, this is my favorite, tool in order to solve these problems. So, what is a cutting plane? Okay, a cutting plane. The formal definition is that it's a linear inequality that cuts some part of the green region, but not of the points of interest, not the red points. So, for instance, this linear inequality is a cutting plane because it's cutting part of the green region of this relaxation, right? But it's not cutting any of the red points, right? Because all these red points satisfy this inequality, right? Are in the correct side of the inequality. But this inequality here is not a cutting plane because it's cutting these 2 points from your problem. Okay. So that's the definition of a cutting. So you cut only part of the green region, but you don't cut any red point. Okay. So let me show you how to use. Maybe you understand it better when you see how you use these cutting planes. So imagine that you want to solve this integer program. So only focus on the integer variables, the red points. This problem is in general super difficult to solve. So what you do is, for a moment, you forget about the red points and you consider only the green region. When you try to optimize over the green region, the relaxation, that's quite easy to solve. So that's what you do first. Okay? So the first step in the algorithm is to solve the continuous relaxation, only the green region. If you solve that problem, you'll obtain a solution, which will be a vertex. So this solution is not a red point, so it doesn't work for you, right? So you want to cut it. So what you do is to find a cutting plane somehow that is valid for all red points, but is forbidding this fractional solution. And once you do that, you obtain a tighter green region, right? But without cutting any of the points of interest. Then you solve your optimization problem again, and you obtain this. Let's say you obtain this solution, which is fractional again. It's not a red point. So you want to cut it off again, using another cutting, right? And they are called cutting planes because they are cutting part of the green uninterested region. Okay, so then in this second step, you obtain a much tighter relaxation. So you solve again only the problem for the green region, and in this case, you obtain a solution that in this case is integer. So then just stop, because that's the optimal solution for your integer problem. Okay. So that's how you use these cutting planes in practice. And all these solvers use this with combination of techniques. Okay. So,
una consulta
yeah.
así más de concepto nomás, que dice que un cutting plane solamente corta, perdón, la idea del cutting plane es que nunca elimine puntos factibles. Pero por ejemplo, si tú tienes un problema, puedes extraer información de puntos que tú sabes que no van a ser solución y cortas eso. ¿Pues eso califica como un cutting plane o son equivalentes si uno hace modificaciones de un problema a otro?
No califica como cutting plane porque por la definición que
claro.
¿cierto? Porque además tú estás cambiando el problema, ¿cierto?
Por cierto, claro.
Entonces, al principio no era cutting plane, pero quizás cuando sabes más información, esa solución ya tú sabes, no va a ser factible, o sea, no va a servir. Entonces, cuando cambias eso, cambian los cutting planes, de cierta forma. Entonces, yo diría que esa sería una respuesta. Okay, thanks for the question. So this is cutting plane algorithm. So maybe the question that you have in mind is, are these useful at all? So let's see. So how effective are these tools? So this is a table showing what happened to the solver, how much slower it becomes when you turn off one of the cutting planes from the solver. And for instance, if you turn off GMI, the solver becomes 2.5 times slower. So instead of 1 hour, it will take 2.5 hours, for instance. Okay. And similar things happen when turning off other cutting planes. Okay, so these actually are very useful. Even when this idea may be simple in some sense because you're just cutting parts, right? They are very effective in practice. Okay, so it makes sense to study them, right? To understand how to discover more of these cutting planes, for instance. Okay, so let's continue. Now that we all know what is a MIP, what is a cutting plane, let me explain to you some of the things I did during my PhD. And essentially, I studied properties of these tools. Okay, I will explain this later. What is this tool? Approaches that I studied. So, but first, before showing you the properties, let me show you, what is the motivation. So, the first model that you can solve, we discovered that, or we tried to solve them and we were successful, are models with linear constraints only. So only these polytopes or polyedra we were able to solve. And we were able to solve them because we have a lot of properties from the tools that were used to solve these linear MIPs. Okay? So we have a lot of knowledge, and this knowledge was useful in order to create algorithms, as the cutting plane algorithm that I just showed to you. Right? But the problem, as you saw, for instance, in the portfolio optimization problem, is that not all problems can be modeled as linear MIPs, only with linear constraints. Why? Because this portfolio problem, remember, that has this risk constraint, and the risk constraint has a variance type of term, and that term was quadratic. So that problem cannot be a linear MIP, right? Not only linear constraints. So we want, in practice, to solve these more complicated MIPs. Okay. So in order to solve them, we need to understand what are the properties of these problems. Okay. So let's see. So this motivates the third question that we asked when I started my PhD. Are these properties that are true in the linear case also true in the convex case? In the more general convex case? The answer is maybe not, because there are some difficulties. For instance, linear MIPs, remember that these are sets defined only by finitely many linear constraints. So they have finitely many of them. General convex set is not defined by finitely many, for instance. So we don't have this nice property. And there are other also properties that here we have that we don't have in the general case. So So maybe we cannot prove the same properties, but at least we can try to do something with it. Okay. So the contributions of my advisor and me and other co-authors are can be divided into two parts. First part is understanding how this visible region, these red points, look like in some cells. That's the first part. And the second part is some properties of this cutting press, some properties of this tool. Okay. So we'll start with the first part. And here, what we did is we gave conditions on the optimization problem, so the visible region, the red points, looks in some sense nice. Okay. And well, this condition was not very easy in practice to check, so we particularized that condition for a particular case of problems. Okay. So conditions that are to have a nice structure and conditions that are easy to check in some sense. So let's start with the condition to have a nice structure. So if you remember, a linear MIP is defined just by linear constraints, right? And you're interested in the points inside. And in this case, if you try to compute what is called the convex hull, so in some sense you only focus on the points inside this polyhedron, and you try to put the lines around it, so something like this. So only I focus on the points inside, and I generate what is called the convex hull. Okay. And in the case of linear MIPs, this convex hull was also a polyhedron, so only defined by finite many inequalities. And that property has consequences in the algorithms that you use to solve MIPs, for instance. So this is a nice visible region, because only finite many inequalities. But in the general case, for convex MIPs, if you try to do the same exercise, but with the points inside the parabola, you start, putting together the dots, right? And if you, I cannot draw it in the slide, but if you go up to infinity, right, because the parabola keeps growing, right, you will figure out that you will have infinitely many of these lines, because there are infinitely many points, right? So this is not good, because I would like to have finitely many only, right? So in general, this convex hull is not a polyhedron in general convex case. Okay, so this is not nice, but one is nice. So I want to understand when a general convex set has a nice structure. That's the question that we asked, or we wanted to answer. And what we did is we found some conditions on this general set, so that this yellow region has finitely many lines, okay, faces. That's what we did, and we also find other conditions, a little bit more general, but let's focus only in this finitely many lines case. Okay, so and then we apply this to other types of general convex sets, these nice properties. Okay, so what we did is find conditions, so we look at the problem that we want to solve, and we said, okay, this has a nice visible region. Okay, that's what we did. So we're understanding better what is the visible region. Okay, but the problem with that conditions that we found is that they are not very easy to check in practice. They're super general. So when theory is super general, it's difficult to apply. So what we did later is to focus in a particular case of convex MIPs that are called conic MIPs. They're called conic MIPs because they are associated to a cone, like you can see in this picture. So this is a conic MIP. The yellow one is the relaxation, and these are the interpoints that you want to use. Okay, for instance, this is a parabola. Well, the picture is not well drawn. I did it, so it's not super perfect, but this is a conic MIP. In this particular case, we found again conditions when this visible region is nice, but the particularity of this condition is that it was easy to check with your computer. I look at the data of the problem. I look at the problem. and the constraints and the inequalities, etc. And I said, okay, this problem will have a nice visible region, okay, and you can do that with the computer in a reasonable amount of time. I mean, polynomial time. Okay, so that's what we did. So nice conditions to have nice visible region and easy conditions to check to have the same thing. That's what we did. And in the second part, we studied properties of cutting planes for MIPs. Okay. In particular, I mean, what is called SP sets and also duality. Okay. So again, imagine that we want to solve this convex MIP because it's a circle, right? And we're interested in the points inside. But let's say if we solve the continuous relaxation, we will not obtain an integer solution, right? Because there are no points on the boundary of the circle. So we would like to cut parts of this continuous relaxation. So we want to find cutting planes. So one way of finding cutting planes is to find what there are called SP sets. So what is an SP set? The yellow one is an SP set. So an SP set is a set, okay, that may contain some integer points inside, but none of these integer points are part of the points of interest. So you can check that this yellow region doesn't contain any point in the circle. Okay? You can see it. And what you can do is you can use this set to generate cuts. So what you do is you remove this set from the circle and then apply an inequality. So let me show you, actually, if you want to understand that better, let me try to draw you a picture of that. So you have your circle, you have your SP set, something like that. I mean, it's an approximation of the picture on the board. And what you do is you remove that part from the circle, so you obtain actually something like this. Right? You remove this set from the circle, and what that generates, it generates a cutting. So that's what you can see in the picture. So with this SP set, we're removing a part of the circle. In this case, we're removing this. I don't know if you can see it on the back, but this like cyan or like blue part of the circle. By adding that cutting. And that cutting plane, you were able to find it by using this thing called SP set. Right? So what you can observe is that, from this picture and that, is that the larger the set, the better the cut you will obtain. Because if you remove from the circle a bigger set, right, you will be cutting more. So remember that we use these cutting planes to approximate better the integer points. So you want to have cuts that remove more from the continuous relaxation, right? So I prefer this cut rather than that one. So that motivates us to study the largest possible SP sets. And these are called maximal SP sets. Okay? So we want the sets that give the best cuts. Okay? And one thing that you can observe from this picture is this SP set is complicated because it's nonlinear, right? It's sort of like a parabola type of shape. But the largest one here, the larger one, right, is easy because we have two inequalities, right, that define it. And actually, that's what happens always. And actually, what we were able to show is that the maximal SP sets, the ones that give the best cuts, are always polyhedral, always sets with finally many inequalities. Okay, that's what we did. And this is nice because that means that the sets that I can use to find cutting planes are easy, right? And like this, all the green ones are maximal, the biggest possibles that I can remove. For instance, this is maximal. This is not maximal because it doesn't contain any point from this region, right? But you can still enlarge it, find larger ones. Same with this one. This one can also be enlarged, so it's not maximal. But the maximal ones are always polymer. And that means that you can use this simple structure, right, in order to find or compute the cutting planes in an easier way. Okay? So this is our contribution, or last contribution with Shantanu. I don't know, it's not the last actually, because I should be one next, sorry. But this is the last one I will focus less on. So, second topic related to cutting planes is duality. Okay? So, you may know duality for linear programs. And if not, let me try to just remind you. So, what is a linear program? A linear program is a problem of this form. Let me do it in this way. X in R. So this is a linear program. So minimizing a linear function over linear constraints. I mean in matrix form, but linear constraints. Subject to no discreteness, no discrete variables. All they are fractional. Could be fractional if they want. And this is the LP primer. And there's also something that is called the LP dual, which is max B transpose X, or subject to I always forget, this is something like which of those equals to C transpose Y non-negative, if I'm not mistaken, something like that. And these are like these are problems that are related. In some sense, you solve this one, you can also solve that one, and you can solve an LP by using both of them at the same time, etc. Okay, so this was known. There was also known that linear MIPs also have some duality results. There are more complicated programs than linear. These conic programs, the conic programs that I told you about, also have duality. But if you mix conic constraints with discreteness intervariable constraints, we didn't know whether we have duality or not. And duality, as I told you, and we try to show you in a few minutes, is very important. It's a very important tool in optimization. Okay, so what we did with Shantanu and Juan Pablo, we actually proved that also these conic MIPs have duality. Okay, and the rest of the talk will be focused on subadditive duality, in duality for these conic MIPs. And the rest of the talk is 15 minutes. More than enough time. Okay, so the outline here for this last part is some introduction and motivation why duality is important, and also I will show you some. I have to show you some notation. I'm sorry about that. And let me, if I have time, I will tell you about results related to this duality. Okay, again, if we finish up to preliminaries, we're super fine. Okay, I mean maybe the organizers can share the slides with you if you're interested, in case we were not able to finish. Okay, so the talk is about duality, or strong duality, what is called for conic MIPs. Okay, so what can I say about duality? As I told you, linear programs, conic programs, linear MIPs, they all have duality. And actually, with Shantanu and Juan Pablo, we also proved it for conic case. Okay. And this duality holds only under certain conditions. And I can also tell you that there are other approaches as well. Other approaches for duality. For instance, I don't know if you have taken a nonlinear optimization class, you have some KKT conditions that sort of related to duality, or Lagrangian duality. And there are other approaches to how to find these duals, not only for LPs, linear programs, but for general conic programs or MIPs. Okay. So in this talk, we only focus in these approaches. Okay? In particular, for conic MIPs, we focus in what's called subadditive duality. Okay? So, but before that, before showing you what is the dual in the MIP case, let me give you some motivations. First, with a simple example, I would try to convince you that duality can be used or could be used in order to find good lower bounds, whatever that means. And then I can also tell you that you can use duality to find categories, which is the motivation from my perspective as a person who wants to solve MIP, right? So motivation one. So let me tell you that you can find good level bounds with duality, or you could. So I gave this talk in Turkey when visiting Burak, and so I tell them about Chilean money, and in particular I learned that they eliminated 1 peso and 5 pesos coins. So all the coins that are relevant here in the picture, all the bills and coins, and this was the exchange rate from 1 peso to Turkish liras and to $12. Okay. So this is the only technical slide in this part of the talk. So let me try to give you this example. I want to travel from Santiago to Istanbul to visit Burak, and I want to buy the plane ticket. And let's say that using a Google search or something similar, I find a ticket that costs 1,200,000 Chileans. Okay, so I want to know how good is my solution. Okay, and one approach to learn how good is my solution is to consider bounds. Okay, so for instance, an upper bound from the minimum possible plane ticket is the ticket that I currently have found. I know that the minimum possible cost ticket will be at most, right, 1,200,000 pesos, right? That you know, this will be my upper. But in order to learn how good is my solution, or how good is the minimum cost solution, I need lower bounds as well. Okay. For instance, if this bound was super close to this one, then I can say that this is a good solution, right? So the question is how to find lower bounds. Okay. So one first possible approach is a triple bound by the negativity of money. So money is at least 0, right? So this first lower bound is telling me that the minimum cost ticket will be at least 0, which is a very stupid bound because, well, this we already know from the very beginning. Okay, so not a good bound. Second bound is, imagine that the money is discrete, so imagine that they only charge me at least 10 pesos because the smallest coin is 10 pesos. So it's better, lower bound than the previous one, but it still is very bad because if you compare this number with that one, it's not telling me anything about the solution I have. Okay. Third possible approach is a smarter bound. Maybe I do a market study. Maybe I know a friend that, or maybe I know a friend that travels very often to Turkey, so he knows, or he tells me that the ticket at least will be 1 million pesos, for sure. Cannot cost less than that. So now we have this less trivial or smarter bound, right? So I know that the minimum cost ticket will be at least 1 million. In that case, I can say, okay, my solution is not bad, or not too bad. Maybe you do this in practice. I mean, when you buy a ticket or something. The price that I found is not too bad. But the question is the best possible bound? I mean, is the best possible ticket that I can find? And in order to do that, maybe in order to find the best possible bound, I can use what is called duality. Okay. So as I said, in order to pick the best bound, maybe it's possible that I can use duality, and maybe it might not in this case. By using duality, I can find or learn that the best possible bound is actually that one. So in this case, I can tell you by using duality that the minimum cost will be between these two numbers, which are the same. So I can say that actually the solution that I found initially was the best possible one, right? I mean, you can think about duality in magic for the moment, but by using duality, I was able to find or to tell you, I mean, my solution that I found is the best possible solution I can obtain. Okay. So we can, as I said, certify that by using lower bounds, that the solution I have is the best possible. So in linear optimization, this duality, as I told you, you have the dual here. So every solution for the dual, you can use it to find a lower bound. For instance, this is your current objective value, and you can say that the minimum cost would be lower bound by taking any feasible vector here and multiplying it by b. Okay. So in linear programming duality, you can use wise vectors in order to find lower bounds. And in the integer case, it's more complicated. Instead of vectors, you have functions, but you can also use it to find smart lower bounds. Okay. So this is one application of duality. You can use duality to find smarter lower bounds. Second motivation, why it's important to have duality, is to find categories. Okay, and let me explain it to you in the case where you have a linear MIP. So linear function, linear constraints, and you only have pure integer variables. All of them have to be integer. And in this case, there is something called the functional approach. What is the functional approach? Is in order to compute a cutting plane, instead of focusing in finding the cut, I will find functions. So you can imagine that this function that I can find is like a machine. I call it cutting plane machine. And how you use it is you look at the data of your problem, the matrix, the vector, etc., and apply the function to the coefficients, and this gives you a cutting plane. So you understand the idea? I find the function, which is like a machine, that given the data, gives me immediately cutting plane. And if the data of my problem changes, I can still use this machine in order to generate cutting planes. Okay, so I use this machine to generate cutting planes. I will show you an example of that. And actually, this functional approach is actually all we need, in the sense that finding cutting planes is the same as finding these functions. Okay, so let's see why finding functions is the same as finding cutting planes. So this is a theorem that is telling you if you find a function, right, that satisfies two properties, then this function can be used to generate cutting planes. Okay. So good. So finding functions is the same as finding cutting planes, or implied cutting planes. Okay, gives you cutting planes. So that's one direction, right? Finding functions gives you cutting planes. Now, what are these subadditive and non-decreasing functions? So these are functions that are, in some sense, almost linear. So g of the sum is less or equal, not equal necessarily than g of u plus u. And non-decreasing means that if your vectors are ordered this way, then when you apply the function, the actual numbers that you obtain are also ordered that way. It's non-decreasing. Right? And if you find any function satisfying these two properties, that function will give you cutting planes. Okay? So as an example of those functions, linear functions are subadditive, right? And if the vector behind the function is non-negative, it will also be non-decreasing, because it's multiplying these inequalities by non-negative numbers. Right? More complicated subadditive and non-decreasing function is a linear function, but instead of considering just a linear function, you compute this number and then you round it up. So if this number was 1.5, Instead of 1.5, you put 2, right? So this function is also can be also used to generate cutting planes. Okay. So let me actually show you in a particular example that you actually can use functions to generate cutting planes. So we are maximizing this linear problem, right? 0, 1 variables, etc. And if you look at this slide for 5 minutes, you will figure it out that the solution of the LP continuous relaxation is this fractional point, 1/2, 1/2, 1/2. Okay, if you look at this for 5 minutes, but believe me for now. So this is not an inter-solution, right? Because fraction, fraction, fraction. So I want to cut that solution. So what I do is to find this function somehow. Somebody told me about this function, for instance. And this function is subadditive and non-decreasing because it's a linear function, and then I round up what is there. So what I will use this function to generate this cutting plane. And remember that the definition of a cutting plane is applying the function to all the columns and to the right-hand side vector. Column, for instance, first column, -1, -1, 0. I apply g to -1, -1, 0. I multiply that for x1. Same for second column, -1, 0, -1. And I apply the function to -1, 0, -1. So the machine is giving me those numbers, right? And so on. So for instance, for the right-hand side vector, -1, -1, so on, I also apply the function. And these are the numbers now, right? Doesn't depend on variables. So this gives me actually a linear inequality. It gives me a cut. And if you use the definition of the function, actually, this is the cutting plane that is adding. So this thing is actually this linear inequality. Okay. And you can check that this point doesn't satisfy this inequality because it's -1/2, -1/2, -1/2, which is -3/2. It's not bigger than -1. -3/2 is less than -1. So this, if you add this cutting plane to your problem, this fractional solution will be cut off. Okay, so good. We can use these functions to generate cutting planes that will remove these fractional solutions. And finally,
y encontrar esa función en particular para que remueva un medio, 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 ¿hay una relación también?
Hay funciones que se conocen. Sí,
Pero, por ejemplo, si yo sé que el punto que quiero remover, o sea, resolví, encontré un medio, medio, medio que es fraccional, ¿puedo construir la función a partir de ese punto para que me lo saque de uno? Porque puedo tener muchas funciones subaditivas no decrecientes que no me corten ese punto en particular.
Yo creo que se puede hacer eso, pero en la práctica uno utiliza ciertas funciones.
Hay
funciones que no dependen de nada. O sea, eso, buena pregunta. So, why finding cutting planes and finding functions is because duality. There is a primal, the same primal, for intervariables. And the dual is a complicated dual. These are functions, not vectors, but believe that exists, this dual. And a consequence of this dual, having a strong duality, is that actually all cutting planes, all possible cutting planes, can be posed or can be seen at this type of cutting planes. So because of strong duality, which I told you that was important, right? You can actually say that all cutting planes are of this form. So and you only need functions in order to find cutting planes. Okay. So as a consequence, define a function, I define a cutting plane, as you saw in the example, right? And actually all cutting planes actually are the same as finding these functions by strong duality. And let me say two things in this -1 minute I have. First, these functional cuts exist and are applied in practice, and actually they are very useful. Actually, this GMI cut, which slows down the solving process by a lot, you turn it off, right? If you don't use it, right? This is a cut of this form. It's a functional cut, and very, very, very useful in practice. And that's it. And the last part of the talk that we don't have time to, this is the second thing I want to say, is not only not for linear MIPs, but for conic MIPs. And what we did with Moran is finding conditions on when these conic MIPs, let me show you how they look like. These conic MIPs, as I told you, they look like a cone and a plane, something like that. These more complicated problems, like the porphyry transition problem, also have duality, okay, under some conditions. And what we do is find new conditions, okay, that we'll use in practice. So, yeah, that's all for now.
Okay.
Thanks for your attention.
Muchas gracias, Diego, por la presentación.
De nada, gracias a ustedes por venir.
Preguntas, sigan el ejemplo del profesor Jara, pueden ser en cualquier idioma. ¿Alguien tiene preguntas por allá? ¿Guido quería hacer algo? ¿No? Acá hay una pregunta.
¿Las funciones objetivos que consideras son lineales?
Sí.
Puede ser...
Si la función es convexa, uno la puede traspasar a la región factible y dejar una línea. Entonces no es tan particular.
Puede que ahí los cortes sean... Generalmente ataca solamente la región factible con los cortes que va a esperar. Pero puede que la función objetivo sí impacte en el...
O sea, la función objetivo impacta en el sentido que con la función objetivo te entrega una solución que posiblemente es fraccional. Entonces tú quieres un corte que te corte esa solución, no quieres un corte que por acá.
Eso. Y en la definición esto de los cortes, uno cuando lo hace de forma iterativa, ¿uno puede sacar un punto que es factible inicialmente o no?
No, porque la definición de los cortes es justamente no puedes cortar ninguno que es factible.
Aunque sea iterativo.
¿Ah?
Aunque sea iterativo.
Aunque sea iterativo.
En el sentido de que puede que una solución... Siempre estoy haciendo cortes sobre la región factible.
Es que tú en cierto partes con un problema original, ¿cierto? Que tiene, digamos, 4 puntos. Si tú fijas tu problema que resolver, que en este caso de este cuadrado en 4 puntos, los cutting planes nunca van a cortar estos 4 puntos. Siempre van a ser así.
O sea, si eso convergiera al infinito sería un cuadrado, serían los 4 cuadrados. Nunca generaría una corte.
Claro, por ejemplo, si esta fuera la solución óptima que uno quiere encontrar, ¿cierto? Uno debería empezar a... Este no me sirve mucho hacer cutting planes, ¿cierto? Uno debería empezar a agregar cutting planes se acercan a ese punto. Pero cutting planes, una vez que tú fijas tu problema, no puedes cortar ninguno de estos 4 puntos. Aunque te entiendo, o sea, yo podría cortar ese para hacer la región más chiquitita, pero no, como uno lo usa en la práctica, nunca cortan estos 4 puntos. Tú lo que podrías hacer es, quizás agregaste muchos cortes y dijiste, ¿sabes qué? Me di cuenta que este punto ya no me sirve, yo sé que no va a ser óptimo, así que lo remueves de alguna forma, pero cuando lo remueves ya tienes otra, digamos que queda una cosa así, entonces tienes 3 puntos. Agregaste hartos cutting planes y esta es tu nueva región factible. Ahora tú quieres resolver este problema que es distinto, ¿cierto? Entonces ahí, en cierto sentido, cortaste esa solución, pero definiste otro problema. Y en este nuevo problema, agregas cortes que de nuevo no corten estos 3 puntos.
Y esos cortes que uno realiza siempre dejan la región convexa y podría ser un corte que fuera...
Siempre deja la región convexa.
¿Eso es por definición?
Por definición, porque hay una restricción lineal. Entonces puedes tener una... Si tu conjunto original era convexo, siempre que agregue te va a quedar algo convexo.
El corte sobre todo
Sí, sobre todo la región.
Diego, una pregunta cortita. A mí me pasa que yo vivo en el mundo de los LP y los LP con alguna variable binaria, alguna variable discreta, claro, sí.
Tú vives en ese mundo.
Claro, para mí yo veo la vida según eso, así como
Ya.
eso ya podéis resolver un montón de cosas. Entonces lo que tú haces es mucho más sofisticado, pero ponte, ¿tú conocías algún ejemplo práctico donde efectivamente se ocupe, no sé, puesto de...
Estas functional approach,
Claro,
en
sí.
el caso en el caso no lineal.
Claro, sí. En el fondo es como que hay aplicaciones que estén empujando eso, o todavía es básicamente cuestiones teóricas, que hay gente que está preguntando por qué sí, en fin.
Hay estudios teóricos de ciertos conic MIPs, donde la gente ha definido funciones que generan cortes, pero no he visto estudios computacionales sobre eso. Por otro lado, cuando en ingeniería eléctrica, por ejemplo, hay problemas que son mucho más complicados que estos, son no convexos, con restricciones polinomiales, etc. Donde tú puedes aproximar ese problema muy complicado por un conic MIP. Y a ese conic MIP tú le agregas los cortes que ahí tú encuentras.
Claro, como los problemas de distribución.
Sí, distribución eléctrica, cosas así.
Ya, súper.
Es lo que también asegura la función.
Claro.
Hoy volviendo a los cortes, ¿hay algún criterio para generar ese corte? ¿Tiene relación con la función objetivo?
Tiene relación con la función objetivo en el sentido de que, por ejemplo, cuando, de nuevo volviendo al cuadrado, con 4 puntos, que es lo único que se dibuja. Si tú estás optimizando para allá, ¿cierto? Vas a encontrar esta solución fraccionaria. Y los solvers ven esta solución fraccionaria, va a ser un vértice porque usan el método simplex, etc. Y basado en estas dos, este vértice está definido por estas dos ecuaciones, ¿cierto? Estas dos líneas. Y hay fórmulas de los cortes que utilizan estas dos líneas para generar tu corte. Entonces, depende de la función objetiva en el sentido de que encontró este vértice, que era el óptimo bajo esa función objetiva. Y ese óptimo te define estas dos ecuaciones, y con esas ecuaciones tú generas tu corte que va a cortar este punto.
¿Esas funciones son como por default? ¿Pero cuáles son como las más típicas?
La función más típica que se usa harto en la práctica es esa que se llama GMI. Que no me la sé de memoria, así que... Pero basado, como te digo, en qué son estas ecuaciones, hay una fórmula que está dado por este punto. Y una fórmula que es como multiplicar y dividir por su número para tenerlo eficiente, no es nada muy sofisticado.
Ya, última.
Me perdí en una parte que mostró una gráfica que iban cortando áreas. Por ejemplo, cuando usted puso la parábola, fue sacando cosas.
Ya, y yo la dejé en amarillo nomás.
Sí, pero antes a eso, hizo como un pequeño triángulo con la restricción que se formaba, que también sacaba.
No era como un cuadrado, parece. Pero sí consideraba puntos. Igual no creo.
Se copió. Ahí está.
No.
Una
Madra. Aquí.
No, madra.
Acá.
No.
Más allá todavía.
No hay más adelante.
Más adelante. ¿Qué había? ¿Hay un círculo? ¿Hay
Sí.
Ah,
La que era más óptima.
con la history.
Ya.
Esa.
Aquí.
La de al lado.
Ya.
Esa es la de la U.
Ya, ¿cuál es la U?
Es que se supone que no tenía que cortar los puntos.
Ya, buena pregunta.
En el interior.
En realidad lo que me interesa son los puntos que están adentro. Los del borde puede tener el borde.
Ya.
Porque lo que en realidad voy a remover el interior nomás. Entonces, por ejemplo, lo que estoy removiendo ahí es... ¿Se entiende? Yo no remuevo, lo que remuevo es... cuando remuevo ese conjunto amarillo me queda esto. Entonces no remuevo el borde.
Ya.
Entonces los puntos que están en el borde igual se quedan ahí nomás. ¿Ya? Eso es... Lo dije bien, como si dice hand waving. Pero buena pregunta. ¿Sí? Excelente.
Pero había otra figura que, sigo que insisto, había una sí, que era como un triángulo.
Esta de acá.
Esa.
Sí, ya.
Bien, ya.
Aquí lo que va a pasar es que, por ejemplo, hagámoslo en el círculo también. Yo tengo, digamos que estoy removiendo esa como bandita que hay. Entonces esta también va a ser free porque quizás contiene puntos acá nomás.
Pero ahí generas cortes por afuera nomás.
Sí, pero los cortes que se van a generar cuando yo remuevo esto va a ser uno por acá
Claro.
que va a cortar un pedacito ahí cortito, y también uno por acá, que también va a cortar un pedacito cortito.
Y ese se
Porque
para el
ahí
espacio
se
complejo.
pararía en el polígono, estaría removiendo.
Sí, porque remuevo solo estas partes nomás.
Como que crea dos espacios
Sí.
diferentes.
No, porque es que no crea dos pasos. Lo que pasa es que para generar el corte uno lo que hace es convexifica, que eso es lo que se llama.
Claro.
Cuando uno agrega expresiones lineales, estás convexificando. Entonces va a tener una región como así, así, que ahí está la bandita. Y va a quedar así, así, como así, y así.
Son dos cortes sucesivos.
Sí. No dije bien cómo se computaba el corte, pero la idea es que... Pero buena pregunta también, porque... Claro, ¿qué pasa cuando lo remuevo algo que está como adentro? Eso. Igual me queda como esa región. Que efectivamente es más chica, es mejor. Buenas preguntas, muy buenas preguntas.
Muy bien. ¿Qué?
¿Quieres hacer la última?
No, yo decía que como por tema de tiempo de repente mejor si hay más preguntas que sea
Personal, sí.
Offline.
Se acabó el tiempo, muchas gracias.
Gracias por venir.
Interesante.
Qué bueno que no presente nada nuevo.